Okay, so we're in the topic of biasing, particularly biasing of BJT amplifier circuits. So what again is biasing? We discussed this last Tuesday. It's establishing the proper operating point or cue point of an amplifier. There are several considerations here. First, we want to establish the bias using the supply voltage. When we discussed the transistor amplifier last Tuesday, we had a separate power supply used to bias the input signal. But that is not desirable because we don't want our circuit to have too many power supplies. So we want to establish the bias using the supply voltage. And we want to make sure that we will not have a distorted output over the input signal range. I'm going to explain or expound on that a little bit further in a while. Of course, the amplifier should have the expected gain. And finally, the bias point must be stable. So let's just review a little bit what we discussed last time. Okay. So I gave a very simple example of an well, you're going to find out later on this is a common emitter amplifier circuit. So I gave a very simple example of an amplifier, and that looked as follows. I just had a VCC, a collector resistor, and then I used an NPN transistor with emitter to ground. And then at the input, I just applied a V capital letter I. And then my output was at my collector. So the output is actually VCE, which is also V capital letter O. So we said that V's of I, this consists of capital V capital I plus small v small I, where we said that this is the bias voltage, and the small v small I, this is the signal we wish to amplify. So you can imagine V's of I to be represented by this. No, you have small v small I, and then you have a V bias, no, which is V capital I, and this is now V capital letter I. Okay. So what did the transfer characteristics of this amplifier look like? No? So we actually tried to recreate the transfer characteristics of this. Okay, what did we say was the transfer characteristics? This is a plot of output versus input. So this is V of O versus V of I. So we have V of O here, and then we have V of I here. Okay. So we said that for small values of V of I, okay, what will be the state of this transistor? For small values of V of I, this will be cut off. If it is cut off, I sub C will be equal to 0, and therefore V of O will just be equal to VCC. Okay. So you have VCC here. So this is your cut off. On the other hand, for larger values of V of I, this transistor will go into saturation. If this goes into saturation, the smallest voltage across it will be VCE sat. So let's say VCE sat is somewhere here. So here VCE sat, and then my output will be this way, no? So for small values of V of I, my output is this way. Now in between, we are going to be operating in active mode. So my curve will look like this, no? Something like this. So here I am in cutoff. here I am in saturation, but here, between here and here, this is active mode. That is active mode. Okay. Now, our operating point should be properly chosen. So let's say this is our operating point. We call this VCEQ. No? Our quiescent point, VCEQ. And VCEQ is the output with VI, capital V, capital V, capital I, acting alone. So if this is acting alone, in other words, wala nito. In other words, V capital I is just capital V capital I. Then VECQ will be our output. Okay, what will happen if I apply now an input signal? So we show that. No? We showed V sub I versus T now. Right? So pinakita natin yan. So now I have an input signal here. Let's say this is my input signal. Okay. The offset is capital V, capital I. That is my bias. That is my bias. Okay. And then the variation, this variation is small v, small I. So as this changes with time, my output, as my V sub I is increasing, will go toward saturation. And as V sub I is decreasing, will go toward cutoff. So my output will be here, no? Going up and down here. So I can plot that, for example, I can plot my output versus time. Okay. When my input is increasing, my output will be decreasing. Okay. And when my input is decreasing, my output will be increasing. Okay. So we can look at it that way, no? Okay, so this is now V sub O versus T in response to V sub I versus T. Again, no? The point, the operating point will be moving down and up as my input changes, causing my output also to change with time. Okay. So what did we say should be taken into consideration? You should take into consideration that you don't want this to be distorted. Now, how might that end up being distorted? So let's take a look, no? Sorry. Let's take a look how that might end up being distorted. So let's say these are my transfer characteristics. Okay, let me draw my transfer characteristics here. Okay. And let's say that I chose a poor value for VCEQ. Let's say nandito yung VCEQ ko. So this is my VCEQ. So what will happen now when my input changes? Let's say my input changes this way. So this is versus time. No? This is V capital I. Note that at this point, nagsasaturate na, no? nagsasaturate na yung transistor ko. So if I take a look at my output, okay, at this point, okay, at this point, my output will be saturated. So I start here. As my input is increasing, this will decrease. However, at some point it will saturate and this will stay at VCE sat. Okay. Now, pagdating dito sa point na to, okay, my input will start going down, so this will now start going up. So that will be okay. And then here it will again saturate. No? Sorry, it's not to scale, no? Something like that. That would be something like that, no? But notice now that this is distorted. That is distorted. If an amplifier has a distorted output, that means we cannot recover the information at the input at the output. Because now this is flat. So that's because we chose a value of VCEQ that is too small. On the other hand, if I chose a value of VCEQ that is too big, now my output tends to become cut off earlier. No? So madi-distort naman siya dun sa kabilang side. No? Okay, it will be distorted in the other side. No? So if VCEQ is too large, what will my output look like? No? This is V sub O versus T. Okay, dito naman siya madi-distort, no? It will go there and then it will cut. And then there, and then it will cut again. By the way, we call this clipping. No? This is clipping. When that happens, we say the amplifier is clipping. So here it clips at the negative, here it clips at the positive. It clips here because it's already cut off. It clips here because it is already distorted. Okay. Any questions? Okay, so that's this, no? Second point, should not have a distorted output over the input signal range. Okay, I'd like to show you the operating point versus the transistor characteristic curves, no? Because showing the operating point on the transistor characteristic curves can provide a lot of information. Okay, so let me just redraw again my circuit here. So this is V capital I. Okay, this is VCE, which is VO, VCC, and this is RC. Okay, if I do a KVL from VCC to ground through the collector emitter, through CE, through the collector emitter, I have VCC minus IC RC, okay, is equal to VCE. And I already mentioned this last time. This is what you call your load line equation. That is what you call your load line equation. And you can plot this load line equation on your characteristic curves. Okay. What will it look like? It's going to look something like this. Now you have a straight line this way. We're at IC equal to 0. So this is IC equal to 0. Your VCE will just be equal to VCC. Okay. And at VCE equal to 0, so this is VCE equal to 0, your IC will be VCC over RC. So this point is VCC over RC. Okay. Your operating point is where the load line intersects with the characteristic curve corresponding to IBQ. So a certain IBQ, let's say IBQ, this is the base current at the operating point. Again, with reference to this, that is the base current that is established by this value of V sub I. No, this is when this is equal to 0. This applied alone will establish a current flowing through here, and that is IBQ. So IBQ is the base current at the operating point. So let's say this is IBQ. So this corresponds to the characteristic curve for IB equal to IBQ. This is now our operating point. This is now our Q point, or our quiescent point. Thus, this will be the value of VCEQ. That is the Q point of your collector to emitter voltage, which in this particular case is also my output voltage. What happens when we now apply a signal small v small I? So we apply that on top of capital V capital I. This signal is going to cause your base current to change. As V sub I is increasing, the voltage across your base emitter will increase, and therefore you expect your base current to increase. So as V sub I increases, your base current increases. Now this is increasing base current. This is increasing I sub B. So this value of I sub B is larger than IBQ, and this value of I sub B would be larger than this value of I sub B. So again, as we apply our input, b small I, that will cause our base current to increase, and therefore our operating point, or our point of operation, will go this way towards saturation. Notice that now this will be the minimum voltage across your transistor. So this is going to be VCE sat. And then the decreasing value of V sub I will cause your base current to decrease, and make your operating point go toward cutoff. So as V sub I increases, we are going up and down, up and down. So that is from the perspective of your characteristic curves, your transistor collector characteristic curves. Yes. Are there any questions? Any questions? Okay. So we said, here, consideration. We'd like the bias to be established using the supply voltage. We don't want to have a separate power supply in series with the input signal. And I already introduced this, and this is your fixed bias biasing scheme. So what is your fixed bias biasing scheme? How do we make now the supply voltage establish the operating point? Well, it's quite simple. Okay, so this is RC, this is VCC. All I need now is a resistor, okay, connected from VCC to the base. Okay, I called this R bias before. Let me just call it RB. What does RB do? RB establishes IBQ. So now you have IB here that will flow. Okay, at the operating point. Okay, at the Q point, we want IB to be, okay, ICQ over beta. That's at the operating point. We want IB to be ICQ over beta. So this is IC. So let's say we already have identified the operating point we want. So for example, tinignan natin to, we already identified that this is the operating point we want. Okay, so let's just say as an example, we want VCEQ desired to be, let's say, VCC over 2. Kunwari na lang, no? VCEQ is desired to be VCE over VCC over 2. Okay. So ICQ is equal to VCC minus 1/2 VCC all over RC. Okay. Or 0.5 VCC over RC. And now we can determine what value of RB to use, because VCC minus IBQ RB will be equal to VBE. This is VBE. VCC, okay, minus IBQ times RB, this is at the operating point, will be equal to VBE. And when we're doing DC calculations, okay, if doing DC calculations, that is our inputs are DC. Our inputs are not time varying signals. Okay, it is okay to approximate VBE to be 0.7 volts for silicon. Of course, we could not do that here. No? We could not do that here, right? Because it is the value of V of I that actually causes I of B to change. So we cannot make V of I fixed at 0.7 because gusto nga natin makita how I of B changes with the changing V of I. So dito, hindi natin pwedeng sabihin this is equal to 0.7 because this signal is actually a time-varying signal whose value varies. But here in DC calculations, usually we just, to simplify, say that VBE is equal to 0.7. Actually, if you want to have a hard time, you could use Shockley's equation for the transistor to determine VBE, based on IB. But you have to know the scale current of the transistor, and of course that would also depend on temperature. Okay, but anyway, so we're doing DC calculation. So I can now, okay, compute for R sub B. Okay, that's VCC minus, in this particular case, if this is silicon, 0.7. Okay, all over IBQ. But IBQ is ICQ over beta. Or so this is just beta times VCC minus 0.7 volts all over ICQ. So in our particular example, for example, we said that ICQ is a 0.5 VCC. So this is beta VCC minus 0.7 volts over yeah, 0.5 VCC over RC. That's just our example. Okay, so this is your fixed bias. So this is how you will compute for the value of RB given a desired value of ICQ. Now, what's the problem with the fixed bias? So the problem with fixed bias is it has poor stability with respect to beta. Okay, the reason for that is this. I sub B is equal to VCC minus VBE over RB. Is that here? Yeah, that's from this, no? That's from this. I sub B is VCC minus VBE over RB. Note that assuming VBE is fixed at 0.7, assuming VBE is fixed at 0.7 volts. Of course, VBE can vary, but assuming it's fixed, I sub B is fixed. Now, I sub C is equal to beta times I sub B. Right? And take note now that I sub C is sensitive or is reliant on beta. I sub C is heavily reliant on beta. If beta changes, IC changes. Okay. Now it just so happens that beta, this varies from transistor to transistor. Okay, even if the same part. Even if it's the same part number, and this also varies with temperature. Beta varies from transistor to transistor, even if it's the same part number, and also varies with temperature. I'll give an example. No, for example, you can have a transistor. Let's say a 2N2222 transistor, whose beta, let's say, is 100 plus or minus 20%. Meaning to say beta can be anywhere from 80 to about 100. So let's say your transistor got broken and you had to replace it with exactly the same transistor. So you bought a transistor exactly the same part number. If your first transistor happened to be on the low side, had beta equal to 80, and then the replacement transistor happened to be on the high side, sorry, this is 120, no? 120 plus or minus 20%. And your second transistor happened to be on the high side, that is 120, then imagine you have a 50% increase in beta. Right? So your ICQ can increase by 50%. if it's from the low side to the high side. So it might have been, your Q point might have been here initially. No? For the same value of IB, remember IB is fixed. That's why you call it fixed bias. For the same value of IB, when you do your device replacement, all of a sudden you see your IC going way up here, increasing by 50% from this point to this point. So that now becomes your new Q point. And because your new Q point now is closer to saturation, then you're going to have distortion. So that is the problem with the fixed bias. No? The root of the problem of fixed bias is this, no? That IB is fixed. IB is fixed. It does not change. A better biasing scheme would have IB changing if IC is increasing. If IC increases for whatever reason, let's say your beta increased, or yeah, your transistor characteristics drifted, your beta increased. If IC increases for any reason, then you'd like IB to compensate by becoming smaller. That would be a better biasing scheme. But in this particular case, that does not happen. IB is fixed. So when beta changes, your quiescent point changes, and it can change quite significantly. So what is a better biasing scheme? Well, it just so happens if I just put an emitter resistor, my bias point becomes more stable with respect to beta. So how will that look like? This is now RC. This is what I'm going to add. I'm going to add RE. Okay. So this is still my RB. Now this is going to be my V sub O. By the way, no, I forgot to mention, how do you apply your input voltage here? I mentioned that already the last time. To apply the input voltage, you capacitively couple it. No? So this is your input voltage. You have to capacitively couple it to the input. No? The capacitor here acts as an open circuit to DC, so that the DC current created here at RB will be totally used to bias this transistor. None of this current is going to go to the input because this is an open circuit to DC. On the other hand, we want this capacitor to be almost equivalent to a short circuit at the frequency of V sub I. If this is a short circuit at the frequency of V sub I, then through superposition, this input voltage is just going to add to the voltage established across the base emitter by IBQ through superposition. And so that now is equivalent, or it will behave equivalent to having your input voltage in series with the base emitter voltage established by IBQ. Okay, so this is now our fixed bias with emitter resistor. It's the same thing. You can apply your input to the base by capacitively coupling it. Note now that V sub O is no longer equal to VCE. Okay, let's take a look at how this circuit is actually, why this circuit is actually more stable. So let's do a KVL along this path, from VCC through RB to the base down to the emitter to ground. So KVL from VCC through RB to B to E, okay, through RE to ground. That's along this path. Okay, so what do we have? This is IB. Okay, you have VCC minus IB RB minus VBE. So this is VBE. Okay, minus IE RE. So the current now flowing here is IE. Okay, is equal to 0. Okay, note, however, that IE is equal to 1 plus beta times IB. This is from KCL. Okay, IE is actually IB plus IC plus, but IC is beta IB. That's why IE is 1 plus beta times IB. Okay, if I compute for I sub B here, substituting this now here, substituting this expression here, and computing for IB, I'm going to get IB is VCC minus VBE all over RB plus 1 plus beta times RE. Okay. And my IC is just now beta IB will just be beta times this, no? Beta times this. Okay, let's take a look at the denominator. If beta is large and R sub E is substantially large, if beta is large, now what is large? No, typical values of beta is large enough, like 100, for example. That can be considered beta large already. So if beta is large and R sub E is substantially large, okay, then we can say that 1 plus beta RE would be substantially greater than R sub B. Kasi kung malaki itong beta to, medyo malaki-laki din tong R sub E, then this product should be substantially greater than R sub B. And therefore, pwede na nating i-neglect to. We can neglect R sub B. On the other hand, we said that beta is large. So beta over 1 plus beta is approximately equal to 1. So this beta over 1 plus beta becomes approximately equal to 1. So we're going to be left with IC is approximately equal to VCC minus VBE all over RE. And if you take a look at this, there is no beta there. It's not dependent on beta. Hindi kagaya dun sa fixed bias dito, okay, where I sub C was highly dependent on beta. I sub C was highly dependent on beta. So, dito, my computation for I sub C shows that it is not dependent on beta as long as I satisfy this condition. That makes my quiescent point more stable. Because kahit na magbago yung beta, even if my beta goes from 80 to 120 like before, my I sub C will stay approximately the same. And therefore, my operating point will not move. Okay, intuitively, how does this work? No? I mean, you can figure it out intuitively. No, sometimes I tell students, try to think it intuitively rather than just rely on the equations, because if you just rely on the equations, you don't really get a feel for what's happening inside the transistor. So try to think of it intuitively. So for example, no, let's take a look at this circuit. Okay. What will happen if, okay, so naka-fix na yung value ng RB, RC at saka RE. That's already fixed. What will happen if I change the transistor, and because of the change in my transistor, my IC tends to become larger kasi mas malaki yung beta nung pinalit kong transistor. So my IC tends to become larger. Okay? If my IC is larger, okay, then IE will also be larger. In fact, if beta is very large, IC and IE are approximately the same. So kung lumaki yung IC ko, lalaki din yung value nung IE ko. Okay, kung mas malaki yung value ng IE, then V sub B will increase. V sub B is the voltage here. That will increase. No? Because V sub B is VBE plus IERE. No? The value of the voltage here is VBE plus IERE. So if IE increases, V sub B will increase. What will happen to IB? Because V sub B is larger, I sub B will become smaller. No? Because the voltage across my resistance RB now will become smaller. No? Pag mas malaki itong VB, mas maliit ngayon yung voltage across my resistor, I sub B will become smaller. So if for some reason I sub C is increasing, that will be compensated for by a decrease in the value of I sub B. So actually there's a feedback mechanism here. The feedback resistor actually is this. This affects the value of IB. No? So the value of R sub E is fed back, no? Is fed back and affects the value of I sub B. So intuitively, that's what's happening. That's why this is a better biasing circuit. Okay, the problem with this is you cannot make. Okay, so there's a constraint. No? You cannot make RE arbitrarily large. Okay, the reason for that is this. Okay, okay, so we said that VCC minus ICRC minus VCE minus IERE is equal to 0. That is KVL from VCC to ground through the collector emitter. No? So VCC minus ICRC minus VCE, ito yung VCE, minus IERE, that's equal to 0. Okay. And so from here, I can get an expression for VCE. Okay. VCE will be VCC minus ICRC minus IERE. Okay. Now, when beta is large, we can say that IC is approximately equal to IE. So what happens here? This now is approximately equal to VCC minus IC times the quantity RC plus RE. That's because I now approximated this to be equal to this. So I can just group RC plus RE together and just multiply that by by IC. And this is now my new load line. That is my new load line. So let's say this was my old load line. So let's say this is my old load line. Without RE. Will my new load line be steeper or will it be flatter? Can someone tell me? Ano mangyayari sa load line ko, bagong load line ko? Is it going to be steeper or is it going to be flatter? Tinatamad ba kayong mag-isip? Okay, my new load line is going to be flatter. So my new load line is going to look something like this. So this is my new load line. This point is VCC over RC, but this point is VCC over RC plus RE. So naturally, mas malaki yung denominator dito, mas maliit yung magiging value ng I of C. So if we're operating at the same, let's just say, we're operating at the same I of B. Dito dati yung operating point natin, let's say this is IBQ. This would have been my original operating point. Now it's going to be here. This is going to be my new Q point. Okay. And the problem now with this new Q point is I am closer to saturation than the old Q point. So the new Q point is closer to saturation. So when my input changes, okay, there's a higher probability that I will hit saturation right away than here in my old Q point. Later on, you're going to see that because of R of E, my gain will also decrease. R of E also causes the gain to decrease. Actually, you can see that partially here. Okay, your gain is dictated by the change in collector current. So if this is my old load line, for the same input swing, my collector current changes a lot bigger, no? Dito sa new load line, for the same input swing, my collector current, kasi ito yung collector current ko, will have a smaller change. And it is the collector current across the collector resistor that establishes the output. So if my collector current changes bigger, then the change in my output will also be bigger and I will have a bigger gain. So that's why this has a larger gain than this. No? Now you're going to study more about that when we take up the details of the transistor amplifier. So that is the problem with just arbitrarily making RE large. But remember, RE has to be substantially large so that this condition will exist. So there's a balancing act that you have to make. You want a stable operating point, but you cannot make RE arbitrarily large. Any question with regard to that? Any question? Okay. The third biasing scheme, which we're going to study, by the way, there are a lot of biasing schemes available. We're only going to take up 3. although in your exercises you might end up encountering more biasing schemes. No? The third biasing scheme which we're going to study is what we call the voltage divider bias. What do we do in the voltage divider bias? Okay, let's start with the fixed bias with emitter resistor. So this is RC, this is RE. And then the fixed bias with emitter resistor, we have a resistance here. Okay. I'm going to change the name. Instead of RB, I'm going to call this R1. Okay. So this is VCC. In the voltage divider bias, I'm just going to add one resistor to this configuration, and that's here. That's going to be R2. Let's show the currents. I'll call this I1. I'll call this I2. This is my IBQ. Okay. This is IC, and this is IE. I'm going to label this point B because that is the base. Let me ask you a question. Okay. Is V sub B equal to VCC R2 over R1 plus R2? Can somebody answer? Is V sub B equal to VCC R2 over R1 plus R2? Yes or no? Isa lang dun sa dalawa huhulaan nyo, yes or no, no? Why don't I do a poll, no? Can you just answer yes or no? I just want to see who says yes and who says no. So I only see 4 people brave enough to provide an answer. Okay, let me ask. I'm going to call someone at random, no? So pasensya na kayo, no? Let me ask Stephen Guerrero. Why did you say no?
Hi, sir. Hello. Rinig po
Yes,
ba ako?
I can hear you. Bakit mo sinabing no?
Kasi sir, I feel like pwedeng magka-implications yung current on the voltage. So, I feel like hindi siya as simple as dividing the voltage.
Yeah, I think you didn't say it exactly the way I expected it to be heard, no? But I think you had the basic idea. Ano yung current that affects, ano yung current na sinasabi mo na causing you to doubt?
Parang ano sir, kasi yung IBQ is there, diba sir?
Yes, that's right.
And
Actually, that's the answer I was looking for, no? This is your voltage divider equation. When can you use the voltage divider equation?
if the circuit is in series.
That's right, no? You can use the voltage divider equation. You can use this voltage divider equation if R1 and R2 are in series. No? Now, R1 and R2 are not in series because by definition, they are in series if the current passing, if the current passing through them is the same. No? But in this case, you have IBQ. If this were open, no, then they would be in series, but there's something connected to the base that is drawing current. So they're no longer in series. So theoretically, you cannot use the voltage divider equation. Okay. However, no, so the answer here is no. No. So not to by the way, the reason why I ask this is a very common mistake that students make when they analyze transistor circuits. Nakikita nila kaagad to, and then by by the nature of the biasing scheme name, they right away apply the voltage divider equation. So the answer is no. But don't feel bad, the ones that answered yes, no, because in some instances you can use this equation. Now, when, no, if I1 and I2 are very much greater than IBQ, okay, then I1 will be approximately equal to I2, and V sub B will now be approximately equal to VCC R2 over R1 plus R2. So dapat hindi sumama yung nagsabing yes, because there's a situation where you can approximately use this formula, and that's when I1 and I2 are very much greater than IBQ. Okay. Now let me compute for V sub B. Let me do a KVL, not compute for V sub B, but let me do a KVL from V sub B through the base emitter to ground through R sub E. So I can do that. Okay. So KVL from B, no, through BE to ground. And I'll have V sub B minus VBE minus IE is equal to 0. No? V sub B, the voltage here, minus VBE. So this is VBE. Minus IERE is equal to 0. And I can compute now for I sub E. I sub E is VB minus VBE over RE. VB minus VBE over RE. Ngayon, itong value ng VB na to, ito, ipasok natin dito. Okay? So what will I get? I'm now going to get IE is equal to VCC R2 over R1 plus R2 minus VBE all over RE. And notice, I sub E does not depend on beta. I sub E does not depend on beta. In other words, if I satisfy this condition, that I1 and I2 are very much greater than IBQ, okay, my I sub E surprisingly will not depend on beta. And since I sub C, well, what is the relationship between I sub C and I sub E? I sub E is equal to for large beta, I sub E is approximately equal to I sub C, right? For large beta. Okay, because ice of C is equal to beta over 1 plus beta times I sub E. Yeah. I mean, you can easily derive that using KCL, no? I don't like you memorizing those equations because those equations are very easy to derive. Basta't alam mo yung KCL, no? You know that IC plus IE plus IC, sorry, IB plus IC is equal to IE, and IC is equal to beta times IB, no? And from that, you can derive the relationship between IC, IB, and IE. But IE is equal to beta over 1 plus beta times I sub c. And if beta is large, then beta over 1 plus beta is approximately equal to 1. And so you get IE is equal to approximately equal to I sub c. So meaning to say, even I sub c independent of beta. Now, what can be more stable than that? I sub c and I sub e are both independent of beta. In other words, kahit magbago-bago yung beta nitong transistor na to, and beta can change because of device replacement or because of temperature, your I sub c will stay the same. Okay, so it's just now a matter of selecting a proper value for R1 and R2 so that I1 and I2 will be very much greater than IBQ. So how do you select R1 and R2? Of course, you have to have a desired value of quiescent current. No? Your starting point is your desired IC. The starting point is the desired IC at the operating point. In other words, your starting point is ICQ. Dapat alam mo yung ICQ na gusto mo. Okay. Now, what is the value of ICQ that you want? Well, that would depend on, let's say this is your output. That would depend on the value of a V sub O you want at your operating point. Earlier we said maybe you'd like V sub O at the operating point to be 1/2 of VCC, so that's a possibility. No? That this you want to be 1/2 of VCC. So if this is 1/2 VCC, it's easy to compute for I sub c. VCC minus 1/2 VCC over RC. The assumption is this RC is given. This RE is also given. So you can compute for ICQ. But that's your starting point, ICQ. Pag alam mo na yung ICQ, then IBQ is just equal to ICQ over beta. Now it's a matter of choosing R1 and R2 so that I1 and I2 are very much greater than IBQ. Now, how much greater? Okay, there's no hard and fast rule. But for designers, there's a rule of thumb. Rule of thumb. Okay, we want I2 to be at least 10 times IBQ. So this is I2, 10 times the value of IBQ. Okay, why don't we want it to be higher? We can make to I2 higher actually. But remember that the higher the value of I2, the higher the power consumption of the transistor. So making I1 and I2 too large will increase power consumption. And you don't want that. Imagine if you're designing, for example, a mobile gadget that works on a battery. Ang labanan ngayon, when you design mobile gadgets that work off a battery, how long will your gadget last on a single charge? So you'd like to keep your power consumption as small as possible. You want your telephone, for example, your mobile phone to last as long as possible. So the circuits that they design in that mobile phone are designed for as low a power consumption as possible. That's why we don't want to make I1 and I2 too large. So usually ito ginagamit na rule of thumb. right before the class, no, I came up with an example. So let's just take an example. I need additional I need additional space. Okay, so let's say I have this amplifier. This is 0.5K. My output is here, V sub O. This is 10 volts. Okay, this is R1. And this is R2. Okay. By the way, no, you still apply your input in the same way, no? If I had my input voltage, I would apply it to my base through a capacitor, no? So it will still be capacitively coupled. In other words, your input ko would be applied this way, no? Connected there. Okay. So let's say beta is equal to 100. Let's say VBE active. The value of VBE in active mode is 0.7 volts, meaning to say it's a silicon transistor. And then let's say that our desired Q point is at V sub O equal to 5 volts. That's just arbitrary, no? V sub O equal to 5 volts. Let's just say that that is the Q point that I want. Okay. So the first thing that I need to do is I need to determine what is my ICQ. So ICQ is equal to VCC minus VOQ all over RC. So this is 10 minus 5, 10 minus 5 divided by 1K. So I'm going to get 5 MA. And my IBQ, okay, IBQ will be equal to ICQ over beta. So that's 5 over 100, 0.05 MA or 50 microamperes. So this is 50 microamperes, 0.05 MA. Okay, so now I want to determine a value of R1 and R2. You can choose any value of R1 and R2. No, but by the way, no. Let me compute for V sub B. V sub B. Okay, what is V sub B? V sub B is equal to VBE, so this is VBE, plus IE times RE. V sub B is equal to VBE plus IE times RE, which is equal to 0.7. We said VBE active is 0.7 plus. Now IE is equal to 1 plus beta times IB. No? So this is 1 plus 100. No? This is 1 plus beta. No? It's 1 plus beta. 1 plus 100 times IBQ. Well, let's just call it IB. No, IB is the value of IB. This is IB at the Q point. No? Times 1 plus beta, 1 plus beta IB times RE times 0.5K. Okay, I know IB. I know IBQ. Okay. So I can compute for this, and if you do the computation, I already did that. This is going to be 3.225 volts. This is VB at the quiescent point, no? At the Q point. That's the value of V sub B at the Q point. So I now have this 3.225 volts. I can choose any value of R1 and R2 that will produce this. Okay, so let's just say arbitrarily, no, na I let R2 equal to 5K. So let's say I chose R2 equal to 5K. So what will be I2? Ito yung I2. This is I1. No? My I2 will be VB over R2. So that will be 3.225 divided by 5K. And that will be 0.645 MA. Take note that this is very, very much greater than this. So I2 is very much greater than IBQ. Meaning to say, this is probably a good enough value of, itong R2 is a good enough value of my resistor to use. So now I just have to compute for what R1 will I need to produce this value of V sub B. So we said that if I1 and I2 are very much greater than IBQ, then we can just use the voltage divider formula. So we have V sub B is approximately equal to VCC R2 over R1 plus R2. So that means that 3.225 will be equal to 10 multiplied by 5K over R1 plus 5K. And if I compute for the value of R1, I'm going to get 10.5K. So these are the values that I choose. Okay, we run out of time, but I want you to do an exercise. So now what does my circuit look like? I have 1K. I have 0.5K. I have 10.5K. And then I have 5K here. And then 10 volts here. No? So remember that beta is equal to 100, VBE active is equal to 0.7 volts, and VOQ is equal to 5 volts. This is the desired. Okay. Now, you can compute for the exact VOQ. Because remember that in determining these resistances, we made this assumption. We made this assumption, and therefore we neglected IBQ. But we can actually compute for the exact VOQ. No? How do you do that? Okay, this is node B. Okay, you can apply nodal analysis to B. So at node B, okay, I hope you didn't forget nodal analysis. You have VB minus VCC over 10.5K. Okay, that is the current going this way, plus VB over 5K. That's the current going this way. Okay, plus IBQ, that's this current, is equal to 0. Right? So this is one equation. Okay. Now, what is your second equation? Your second equation can be KVL along this path. No? Your second equation is now VB is equal to 0.7 volts. No? That's VBE. Okay. Plus 1 plus beta IBQ times 0.5K. So this is actually 101. No? 1 plus beta IBQ times 0.5K. This is your equation 2. So you have two equations, two unknowns. You can compute for the exact IBQ and the exact VOQ. Right. So this is now checking how close we are to the exact values. Now not simplifying the solution, no? Because we simplify the solution by just saying VB is approximately equal to the voltage divider equation. But here we did not use the voltage divider equation. We used actual nodal analysis at B, no? Taking into consideration the value of IBQ. So we don't have time to do that now, but you can do that on your own, and then you can compare now. No, how does the approximated value compare with the exact value when I actually set up this particular circuit? You're going to see that there's some difference, but from the perspective of biasing, the difference is not material, no? Because when we bias a transistor, we're not very sure of all of the parameters of the transistor anyway. And so that difference is not going to be material. I'm going to stop here. So that ends the discussion on biasing. So again, just to summarize, what do we do in biasing? We're really just trying to establish the operating point. And when you establish the operating point, all your calculations are DC calculations. In other words, we forget first the AC component of the signal that is fed into the amplifier. We just kalimutan muna natin yun. We just consider the DC component. So all of your calculations are DC calculations. And like I said, when you're doing DC calculations, it's okay to just approximate VBE to be equal to 0.7 for silicon. So that is biasing. That's why if you take a look at the exercises, for example, in the text, no? The biasing exercises are really all just calculate based on the circuit, calculate what is the value of IC or VO or whatever. No? Yun lang yun. Okay. So any questions? So next Tuesday, what I'm going to discuss would be the different transistor amplifier configurations. You're going to find that there are three general types of amplifier configurations: the common emitter, common base, and the common collector. So we're going to discuss all three configurations. And then the Thursday after that, which is the last day for module 3, we're now going to discuss the small signal model of the transistor. Just like we discussed the small signal model of the diode, may small signal model din yung transistor. And actually, it's the small signal model that we will be using for the rest of the course. That is in characterizing amplifiers. Okay, so I'll end the session as soon as the last person leaves. Yeah, that's all.
Thank you, sir.
Thank you, sir. Bye
Thank you,
po.
sir.
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 Thank you
Okay.
po.
Thank
you po, sir.